This meeting is being recorded.
Let's begin a discussion of Chapter 5 and the topic of stereoisomerism. So in the past, we've seen constitutional isomers. Now we're going to introduce another type of isomers. So we've seen that isomers have the same molecular formula. So all types of isomers need to have the same molecular formula, but there are two general types. So we have our constitutional isomers, where we have different constitution, different connectivity of atoms, but we still have the same molecular formula among all constitutional isomers. Then we have this new term of stereoisomer introduced, where we have the same connection, so each atom will be bonded in the same pattern, the same connectivity, but in three-dimensional space, this different spatial arrangement will occur. So we'll take a look at how we can identify that. One way is if we have a ring structure, we'll see that we can have this dividing line here where we separate the plane above the ring and the plane below. So if we have two substituents on our ring, for example, here, and they're both above the plane, we would say that this would be a cis stereoisomer. These compounds are both 1,2-dimethylcyclohexane, but as you can see, one has both of those methyl groups above the ring, and then over here, we see one above and one below our ring. So that would be the trans isomer. So both groups on the same side, cis. Both groups on opposite sides would be trans. And to give the appropriate IUPAC name, we're told that we would just add cis or trans in front of these compounds to give the full unique IUPAC name to each. So another way of looking at cis and trans isomerism is if we have a carbon-carbon double bond. We can also see that this plane can be inserted between our double bond. So we could have groups above or on the same side of our double bond, and then we could have one group above or below. So in our first compound here, this is a butene, right? We have 1, 2, 3, 4 carbons total, just like we have over here, 1, 2, 3, 4 carbons total. So they're both butenes, the ending ene because of that double bond. So they're both alkenes. And notice that we have 2 given as a locant for where our double bond starts. So that's the same in both compounds. The only difference we see here is the spatial or 3D orientation of these two groups here. So we have both on the same side in our cis 2-butene, and then we would have the two groups on opposite sides in our trans 2-butene. So not only can you name ring structures as cis and trans, you can also name alkenes as well. So let's take a look here and see if we could identify these pairs of compounds as either constitutional isomers, so they would have different atom bonding patterns, but the same molecular formula, stereoisomers, so they have the same atom bonding pattern, but different spatial arrangement. Or are they identical structures? Can we rotate a bond or rotate our whole structure and find that we have the same thing? So we're told here that the answers are on the next slide. So take a moment here and look at these pairs and see if you can see the relationship. But I will review why each case is which on this slide here. So what we see in our first pair here is that we have this OH group in an equatorial position here, and then we have the same single substituent in an axial position over here. So this is the same compound, we've just performed a ring flip. So this carbon here has moved up here. So these are identical structures. Our second pair, what we see is that we have an axial substituent here, and then in this case, we have an axial substituent and we have an equatorial with this hydroxyl group. So both are disubstituted cyclohexanes, both have the same connectivity of atoms and the same substituents, but we can see that due to their positioning as either axial-axial or axial-equatorial, these would be now stereoisomers. This next one down here, this is probably pretty obvious. If you were to count all the carbons, all the hydrogens and oxygens, you would see the same molecular formula. So you know that they are some type of isomer. And I said that it's obvious because we have a cyclic structure here, and then we have an acyclic structure here. So we're told that they have to be one of these types of isomers. So we would default to the constitutional isomers because we know that they do not have the same atomic bonding pattern. Let's go over to the right-hand side. Now this top set of molecules here, we see that if we were to rotate one around, we would end up with the same structure. So this original structure would be retained or regained if we were to give this a 180-degree rotation. So these would be identical compounds. And then our last pair down here, we see the same number of carbons, we see one double bond, so we'll assume that we have the same number of hydrogens. You can always count to confirm that, but we would have to, or we would not have to break bonds to generate these two isomers. Rather, what we see is that our we have some hydrogens here as well, so maybe this will make it a little easier to see. One is our cis isomer, stereoisomer specifically, and then this guy over here would be our trans stereoisomer. So we have one more slide here to review and see if we can now determine the stereochemistry as either being cis, trans, or neither. So recall that we need to have either both groups or on the same side of the plane of our double bond or one on each side. If we have both groups coming off our same carbon within a double bond or within a ring, that would be neither cis nor trans. So